thank you. So let's start. So welcome Kisun Lee from Georgia Tech. So he'll speak on certifying solutions to a square analytic system.
Yeah, thank you. Thanks for having me. And
is the video on?
Yeah, he said that you already recorded. So I'm really happy to give a talk in here. So today I want to talk about certifying solutions to a square analytic system. So in terms of research, I'm interested in certifying the output of the numerical algorithms. So in this talk, scope of today's talk is about certifying the numerical roots of the square of the analytic system. So for example, let's say that you have some system equations and you're going to solve that using some numerical solver. Then you're going to get a numerical root, probably that is really close to your exact root, but of course we don't know where the exact root is. But and actually that numerical root cannot be your exact root. So we want to check that whether this given approximation is good or not. So before I start our talk, this talk consists of two parts, so which is the works that I've done recently. So I think I need to introduce my co-authors first. So first half of the talk is about certifying the regular root, which means that we deal with the root with the multiplicity one, simple root. So it was done with Michael Burr, who's a faculty in Clemson. I think. Yeah, so this screen does not work with the.
He was a student here in Krawczyk.
Yeah, I know. Yeah, right. Yeah, so he was also a student in NYU. So I mean, a faculty in Clemson University, and Anton Lakin, who's my advisor in Georgia Tech. So second half of the lecture, second half of the talk is about multiple roots. So when we think about the multiple roots in here, it was work done with Dan Li and Li Hongji. They are both in China. Okay. So before I introduce the main part, I think I need to remind you what is the meaning of the certifying the solutions. So let's say that you have some solution, you have some system equations, and we solve that using some numerical solver. Then we're gonna have this kind of point x in here, which is just the numerical root of the solution obtained from the numerical solver. Of course, we don't know where the exact root is, but from this numerical root x, we are gonna obtain some compact region which is called capital I in here. This is the region, compact region, which is obtained from this x in here. And we're going to apply some algorithm to check that this x star, which is the exact root of the original solution, is contained inside the capital I in here. And also, not only this one, we also say that we want to say that other roots of the system is not contained inside this region, which means that we want to prove the uniqueness of the root also. So let me talk a little bit more rigorously that let's say that we have some compact region which is probably obtained from the numerical root. Then we're going to apply some algorithm and we want to check existence and uniqueness of the root inside our capital region. This is the meaning of the certifying the roots. So when we deal with the multiple roots, this same concept will be also applied. Okay? So I mentioned about the analytic system in here. So in the first half of the talk, we will focus on some special kinds of the analytic system. So as an example, let me just give you error function in here. So this is an analytic function. So this second sentence is not designed to be read, but I just want to say that this error function satisfies some differential equation with this given initial value conditions. So with this error function, we're going to consider some square analytic system. So in this system, we have two variables and two equations. So this is a square system. But I want to, so this is the analytic system, but I want to write down this kind of analytic system in a little bit more general way. And also we want to give arithmetic operations onto the functions that we use in the system in a way that we are allowed to compose our function or add function or multiply function. So in other words, I will just write down this capital F in here. So now we have 4 variables and 4 equations in here. We have 2 equations which are polynomial. But can you read this? Yeah. So third equation is corresponding to the first error function in here. And fourth equation corresponding to the second error function in here. So if you plug in T3 and T4 inside your second equation, then exactly you're going to get this system. So we want to write down this kind of general form of the system equations. So analytic system in the first half of the talk is about this kind of system. Okay. So,
could you go back to the slide? So you said certified existence and uniqueness.
Yeah, right.
Can you replace certify by prove? So certify here is the meaning of has the meaning of proof, right?
Yeah, I mean, we can guarantee that there's inside the compact region, there's only one root inside of the system.
Can you fail? That's the question.
Oh yeah, of course, right.
How can you be sure that you will always, or under what conditions you know you will succeed?
Oh, so for example, like in alpha theory, if you just compute the alpha value, which is bigger than the summation number, then we can say that, of course, that root can be more refined. So there's some kind of a signature that we can check whether the certification works or not. So of course it can fail. Then in that case, we should have more higher precision to our numerical solver or something like that.
What do you mean by failure?
Failure means that
Gives no answer or gives no
gives no answer. Gives no answer. Yeah. So of course it may be an approximate solution, but we don't know. It means fail. Yeah. Failure of the certification. So basically what I want to say is in this talk is, so we want to certify given approximation x in here, which is a probably numerical root. And when we will kind of consider this capital F in here, we have n plus m variables and n plus m equations. First n equations are polynomial with n plus m variables. And the last equations are, we have ingredients in here. We have each gi function in here. So this g sub I is a univariate analytic function. So in the first half of this talk, we're going to call this as ingredients. Okay. So and for the further notation, we have x star, which is a notation for the actual root of the capital F. So with this notation, what we want to do is when we have some compact region capital I, we want to check the existence and uniqueness of the x star inside our capital region I. This is what we want to do.
So the regular root, what's the meaning of this?
A regular root means that multiplicity is 1. Just a simple root.
And how do we define that for an analytic system?
What do you mean by how do
What
we?
is the multiplicity? Could you explain what the multiplicity is?
Okay, so in order to define like analytic multiplicity in an algebraic way, probably we can think about the Taylor expansion of each system, each equation inside of the system. Then we're gonna have the same multiplicity structure. So multiplicity of that root can be also multiplicity of this kind of root, but it is just a usual sense of the multiplicity. Like
Which is what?
can you say it again?
So what is the usual sense of multiplicity?
Like, okay, so probably which is obtained from the Hilbert function. So Hilbert function. So I mean, what I can like say about like multiplicity in here is like, so maybe taking the Taylor series expansion would be the best answer that I can give. Like, if you think about the Taylor expansion, then analytic system become
Taylor series expansion of what?
Of the analytic functions inside our system.
Of the equations.
Yeah, of the equations, yes. Then it's gonna be the polynomial system. Then our system becomes a polynomial system because we just
infinite.
Oh, of course we're gonna truncate that. Up to like a finite. We just compute the finite many terms of the Taylor expansion. So if we have like this kind of error function, then we just consider finite many terms of the Taylor expansion.
How many?
High enough, but it is actually known that how high it should be. But when it is high enough, then the multiplicity structure is the same with this analytic system locally. Then in that case, we can also define multiplicity in terms of the polynomial system sense. Yeah, I mean that's the best answer that I can. Yeah.
Could you explain a little bit how the equation can rewrite as a ft1 up to t2?
Oh, I see.
Up to t4.
So instead of writing down this error function in here, we just take this as a t1. We just introduce more variables. This analytic functions many. So we have two analytic functions in here. So we introduce two more variables. So T3 corresponding to the first order function with the first variable, and the T4 correspond to the second variable. So if we have m equations in here, m equations inside our system, then we introduce m more variable, and inside our first polynomial system, we get n plus m variables. So,
Okay.
okay. So let's look at some previous works about this one. So when we have an ingredients of polynomial, then our capital F is just a polynomial system. And the algorithm for this kind of certification was implemented by John Hauenstein and Frank Soperly in 2012. When we have an exponential function, for example, like trigonometric function or hyperbolic function, then the algorithm for certification was implemented by John Hauenstein and Victor Lewandowski in 2017. They are both implemented in Alpha Certified. So they used alpha theory to certify that. Okay.
And so it's implemented in Alpha Certified. So what is Alpha Certified?
Oh, this is the software.
Software.
So you can just type in, you can just plug in like a system and approximate solution, then it will gonna give you the answer. Yeah.
Standalone?
Yeah, it is standalone. So in this work, we're gonna use two different methods to certify the solutions. The first one is a Krawczyk method, and the second thing is the alpha theory. So Krawczyk method is some kind of interval extension of the Newton iteration. So it combines an interval arithmetic and the Newton method. So let me just introduce what is the interval arithmetic a little bit more briefly. So we want to, in order to have some conservative region when we do the computation, we just give some arithmetic operations in between interval. So we can just add interval, multiply interval, subtract, and divide interval. And the alpha theory is actually well-known Smale's alpha theory. So it certifies the given approximation converges quadratically to the actual root or not. So let me just tell you about what is a quadratic convergence. So we first define this Newton operator. Then we can also apply this Newton operator multiple times. Then if kth iteration of this Newton operator satisfies this inequality, then we call that this given approximation x converges to x star quadratically. Okay. So in this case, we call this approximation x as approximate solution for x star. So let me just look at this Krawczyk method a little bit more with detail. Let's say that we have a capital F, which is the square system, which is differentiable. This I is this is the region that we want to certify. So it's going to be given as an interval because we want to do interval arithmetic. Then with this I, we're going to think about which is called interextension, which is denoted as the square of this capital F of capital I. So this is just the collection of the values of the capital F over some interval.
And again, to certify an interval means that the system has a unique solution there.
Yeah, inside this interval, inside this given interval, given input. Okay. Yes, and so if we have a polynomial system, it is quite easy to compute this kind of interval extension because we can just plug an interval inside our variable. But if you have analytic functions, probably slightly more complicated. So y is just any point inside our interval. Probably we can, inside our implementation, we just choose a midpoint of the interval. And what capital Y is an invertible matrix. And then we can, using this ingredients, then we can define a Krawczyk method or something like this. This is an interval operator, so actually they're just an interval box. Then using this Krawczyk operator, we have the theorem which is suggested by Krawczyk in 1969. So the first one is, let's say that x inside our capital I is actually the root of this capital F. In that case, x is also contained inside our Krawczyk operator. This is the first one. But next thing is important. So if your Krawczyk operator is contained inside the original input I, then we can say that there is a root of the capital F inside our original input I, so which proves the existence of the root. And also, the last one is, if we satisfy this additional norm condition, then we're gonna make our Krawczyk operator something like a construction map. So if you apply this Krawczyk operator multiple times, it's gonna be interval gonna be smaller and smaller. So we can also prove the uniqueness using this one. And also, when we deal with the interval, it is quite natural to think over the real. So we can also switch this thing over the real. So when you just switch this to the real, then we should change our norm condition in here. But everything just works the original, just the same in the same way. And actually, this is the original version of the Krawczyk theorem, because yeah, it is quite natural to think about interval over the real. Okay? So this is a Krawczyk theorem.
So what's the difference in the real and the complex version?
Oh, we only have a difference in the real this coefficient of the norm condition. It because when we deal with the complex interval, we should have an imaginary interval part. So it gives us at most square root of 2 part.
Doesn't depend on n. It's not like square root.
Oh, it does not
n.
depend on that because we are just dealing with like a
infinity norm.
yeah. Yeah, so yeah, this norm is actually the interval norm, which is defined as a maximum value, which is infinity norm. So as a one more remark, if we have a capital F, which is hard to compute, when the capital F of y is hard to compute, we can also think about this interextension for this capital F of y. Then we can also define this new Krawczyk operator. If you replace everything with this new Krawczyk operator, then everything works nicely also. Okay. So this is all about the Krawczyk method. Let me also introduce about alpha theory. So let's say that we have a point x in here. Please remember that we have a coordinates x1 through xn. Then with this return iteration map, we can define these 3 parameters. So first one, alpha, is obtained by the multiplication of the beta and the gamma. Beta is just the length of the Newton step. And gamma is obtained by the supremum of inverse of Jacobian times kth derivative and divided by k factorial and take the k minus 1 root, which is really complicated. But anyway, alpha theory says that when the value of alpha is less than this number, then x converges to x star quadratically. And also we have a region which contains x star. So distance between x and x star is less than or equal to 2 times beta, which means that we have some concrete region which contains x star uniquely. So we can also use this alpha theory to certify the root. But the problem is, of course, this gamma part, because we have a supremum for the infinitely many k values. And also, if you look inside, we have a kth derivative, which is k-symmetric tensor, which is computationally really expensive. So usually, we find upper bound for this gamma value, and we use that upper bound instead of that. So natural question is, do we have such upper bound when we have an analytic system? And we now suggest the theorem in here. So let's say that we have univariate analytic function, which that I called ingredient before. Let's say that we have gi. Gi corresponds to xi, which is the coordinate of x in here. So then we need 2 oracles, which is the first one is a capital Ri. This is the positive value, which is slightly less than the radius convergence of gi. So gi is the analytic function. We can think about the series expansion. Then we can also get the radius convergence. The positive value, which is slightly less than that, will be called as Ri. And mi, this is just upper bound of this absolute value of the analytic function over some disk. So when we have these 2 values, then we can also compute this upper bound for this gamma. This mu is a condition number for f and x. So we can also, so this is the upper bound for this gamma in here. So we can use alpha theory actually, okay, without computing this gamma value. But let me just go back to our original 2 method because there's some problem. If you remember the Krawczyk method, Krawczyk operator, we need to find these 2 interextensions. Also, if you see the alpha theory, we need to find out capital Mi and capital Ri. So capital Mi is just like I said before. This is the maximum value of the analytic function over some disk, and capital R is comes from the radius convergence. So the question is, how can we get these 2 oracles? So we need to answer these 2 following questions. First one is, how can we evaluate analytic functions at a point or over an interval? And the second question is, how can we get the radius convergence? Okay? If we can answer these 2 questions, then we can also get these values, get this red part in here. So we decided to look at some special case of a special family of the analytic function, which is called definite functions. So let me just introduce what is definite functions first. So define function is a class of the analytic function which is the solution of the linear differential equation with the polynomial coefficients. So if you have g of t, which satisfies these differential equations with the given initial value condition, it will going to be called as a definite function. So this definite function is quite well-studied area. So Van der Hoeven in 1999, he suggested an analytic continuation algorithm which is using for the approximate the value of the definite function. And also because this definite function is an analytic function, we can think about the series expansion. In this case, we call this as a major series. So Metzger and Salvi presented the algorithm for the major series for the definite function. So we can also extract the radius convergence from this major series. So they are both implemented in these two softwares. So in our experiments, we use the Sage method implementation. Okay. Now it is time to do some experiments. So the point is now we can certify the roots of the system when we have a definite functions as ingredients. So I will show you some experiments. The first one, so in order to do with some examples, we just consider some optimization problem. So in order to make some optimization problem, we consider two different ellipses in here. So because we have two, let me just introduce the variables in here. So EI in here is the eccentricity of ellipse, and BI is the length of the minor axis of the ellipse. Yes?
So, quick question. So you mentioned definite, but is the question completely trivial if just restrict to polynomial systems?
Yeah.
It's completely trivial?
Of course, you should know how to find the upper bound for the gamma. So, okay. This upper bound for gamma will be different if you have a polynomial system. Probably tighter than this one.
So let's see, this bound of gamma. Can we go back to the definition of gamma again?
Yes.
Okay, so it's this guy. So it's k derivative divided by the first derivative times k factorial, and then you take the k. Okay, right. So, and then let's go back to your approximation. So this mu is condition number, right?
Yes, right.
Which is basically like f prime over f prime, something like that.
It is obtained by like a norm of f times norm of the f inverse or something like that. Yeah, and then
Right, and norm
addition.
of f inverse. Okay, yeah, that's the condition number. And then what's the first term and the second term? What are the two terms? What's the m?
So this terms covers the degree of the polynomials. So if you think about the capital F that I suggested before, we have a bunch of polynomial system in the top. So this part covers that part. So the ingredients part, which is analytic equations, they are going to be covered by this C.
And the CIs are
CIs will be obtained from this one, which is obtained by Cauchy integral.
Cauchy. So it's interesting that you have 1 over Ri
Yeah.
for the, but it's like 1 over Ri square, right? Because there are Ri twice.
Yeah, and
Why is that?
oh, these are obtained from the Cauchy integral, but yeah, I mean but I actually don't remember how exactly get this. Why we need to have two terms in here. But if you think about the derivative of this kind of, so there are several ways to compute this kind of CI. So if you think about the derivative, oh, I see. So let me just explain this way. Because this is obtained from the Taylor expansion, so it obtains from the each term in the Taylor expansion. And this is obtained from the Cauchy integral. So we can also find this CI using the derivative of the GI. In that case, we're gonna increase this RI gonna be scalar or something like that.
So this Ri square is kind of essential, you're saying? You can't get rid of it? Can you imagine getting only a single Ri?
Only single RI?
Right. Rather than Ri square.
Well, when we have some special analytic system, maybe we can, but not in general.
What is xi?
Xi is the coordinate for x. So each coordinate we're gonna have a corresponding analytic system. So we're gonna consider those as.
Can you go back to original? I'm confused about what you call ingredient.
Ingredients is
Let's see what's the ingredient there. Okay, this one.
here. So we have this function. These analytic functions will be called as ingredients.
I see.
So we have two terms inside our bound. So first term covers this polynomial part, and second part will Ci part will covers this analytic functions part.
They're basically given by the definite functions. You're talking about definite.
Yeah.
That's why they have this form.
Yeah.
And how? So have you looked at any industrial applications? And where the choice of definite comes from? So
What is application?
What concrete systems do you have in mind that you will apply this to?
Oh, so
And the error function, was it an artificial example just to demonstrate, or it comes from some natural problem?
we just consider as just an example.
Artificial example.
Yeah.
Teaching example.
Yeah, right. We couldn't actually when we work on this. I mean, even for now, we actually couldn't think about any concrete example in situation yet. But maybe if we only work with like a trigonometric function or something like that, then probably we can work with like arts problem, like a motion arm machine with the motion arm problems, like something like we can also work with something like that. So because trigonometric function is also definite, so you can think about the motion arm problem using
Robotics, you mean?
Yeah, robotics. Yeah.
I think it's good actually to try to get into some actual
But
examples from the
the
real
reason
world.
that we didn't choose the robotic example was because it was done by. It was done by John Hamstein and Victor Lewandowski in this paper. So we actually compare with this result also. So sometimes we can have our bound can be better than this bound. Sometimes. So there's actually a result in the paper. But yeah, actually we didn't use that concrete example as our example inside the paper.
Remy, I thought you want to make a comment.
No, just you said if we are able to do it for trigonometric functions, we can do it for robotics.
Mm-hmm.
But I mean, trigonometric function is way simpler than
Definite function.
the definite function. So what additional things do you have with definite functions? But
Are you asking about what kinds of functions are there?
I think maybe you're thinking in robotics, sines and cosines can be replaced. They're all really algebraic quantities.
yeah, but we also know how to evaluate, because here, so at least for evaluating your Krawczyk operator, you just need to have an interval extension of those functions.
Mm-hmm.
But we know how to do it for trigonometric functions, we can do it. Right?
Yeah.
Of course. But okay. So, but let me just put in this case. So their work only works with alpha theory. So Krawczyk method was first used in this work. So Krawczyk method. Even though it was quite well known in the probably numerical analysis people, but it is the first time that using
It's
this
very
Krawczyk
standard
method.
in interval arithmetic.
Yeah, right.
Numerical people, they don't know these things.
Okay, I see.
But interval community, of course.
Yeah, so in terms of like our algebraic geometry people, it was the first time they're using this kind of interval method to certify the solution. Even for the polynomial.
Can you say it again?
Oh, so in the applied algebraic geometry people, it was the first time that they're using this interval arithmetic to certify the roots. Even for the polynomial
Just to
system.
certify the roots, but some people use Krawczyk method to find the roots.
Oh yeah, of course. Yeah, of
That's
course,
why
of
it's
course,
all-
of course. But yeah, but in terms of certification, it was the first time.
Yeah, but if we know how to use it to find the roots, we know how to certify it.
Yeah, yeah, of course. Yeah.
But yeah,
Yeah, right.
anyway,
It is.
thank you.
Yeah. Okay, so I need to skip. Okay, so let me just go back to our optimization problem. So now we have this EIBI, because we have two ellipses in here. We have E1, B1, and E2, B2. So now we have this objective function, and we want to maximize them subject to these three constraints in here. So we have E of t in here, which is given in here. So this is which is called the complete elliptic integral of the second kind. So this is not even algebraic. So this is, even though this is analytic, but not even algebraic. So this is kind of a quite complicated definite function. So it satisfies this kind of inequality, this kind of differential equations. So anyway, with this using function, we want to solve this optimization problem. But in order to solve this one, we just consider the Lagrange multiplier. So we introduce three more variables, lambda 1, lambda 2, and lambda 3 in here. Now we have 7 equations with the 7 variables, so this is a secure system. Now we solve this system using some numerical solver. Now we have this approximate root. Then we were going to use a Krawczyk method and alpha theory to certify this root. So let me just start with alpha theory. So as we mentioned before, in alpha theory, we need to find that the upper bound for gamma, and we also have this gamma value, upper bound for this gamma value in here. And we need this capital R. So in this case, we use the radius convergence as a 0.005, which is less than radius convergence. Then in this case, alpha theory is less than 0.035, which is also less than this number. So alpha theory works for the certification. And Krawczyk method. So in order to think about the Krawczyk method, we just consider the interval with the side length, which is 2 to the negative 10 to the 2, which contains this root. Even, of course, this is a 7-dimensional root, but because dimension is too narrow to contain that, I just only draw 2 dimension. Anyway, we consider this given input compact region capital I. Then if you compute Krawczyk operator, then you're going to be contained in here. So we can also certify the root using the Krawczyk method. Okay, so actually this length was 10 to the negative 13 or something like that, which is really smaller than this original input.
What you're saying? Krawczyk is better here?
Oh no, this Krawczyk operator is much smaller than this original input. I didn't mention about which one is better.
So okay, you certify using, let's say, alpha.
Oh yeah, this is alpha theory.
Alpha theory, if you take radius to be 0.05, that's the radius of your box, right? Of your I, your region I.
Oh no, this is the radius convergence for the.
Right. Okay.
Yeah.
Then how small do you have to be your box in order for this to apply?
Oh, so it depends. Actually, when let me just when R is too small, then this value will be bigger. So when R is too big, then this MI will be bigger.
Right.
So we need to choose really proper R.
So what did you choose in order to verify? You have a very concrete example, right?
Yes.
This optimization problem.
Yeah.
And you want to certify a particular root, a particular solution, right? And if it's certified, then it really proves it is optimal. Is that right? And using this, you managed to certify that solution?
Yeah.
What did you choose? That's what I'm trying to say. In order to apply this.
You mean this approximation?
Right.
Approximation?
Right.
How did I choose this one?
Well, as you said, you have to choose R appropriately so that it actually certifies it. You do have a box that you have a candidate solution, right? And now you want to certify it. So what number did you choose to certify?
Okay, but this R is not related to the box which containing this.
Oh, I understand.
Yeah.
But you have to choose something.
Yeah,
So
right. How did I choose this one?
I don't care about this R because this is
Yeah,
not
yeah,
R.
yeah, yeah.
I have a particular root that I'm trying to certify.
Mhm.
You could certify using this alpha method.
Mhm.
How do you choose your parameters so that you could actually certify? Right, you have to choose something. I have a box. I say this contains a solution. Certify using alpha method. So how did you do it? Yeah. Very concrete. This is a numerical example. I'm just asking how do you choose the numbers or what are the numbers that allows you to certify?
But you're asking about the region that we can.
Yeah,
Yeah.
whatever.
But so if we have this kind of alpha value, of course, then we have a beta value or so. Then from the alpha theory,
Yeah, that's
we have this kind of region.
yeah, but that's not.
Actually, you don't need a region in input.
Yeah, we don't need a region
the
to.
size of the region you can certify. This is the meaning of this. You take the approximate solutions, and with this you get the radius of a region around this solution.
Right. So did you certify? Did you succeed to certify using alpha theory?
Yes.
And what was the number you picked that you? I mean, you have to have an approximate solution.
Right.
And how approximate do you have it? This is your.
Yeah, approximate solution that we used.
Okay, so you're mainly interested in the E1, E2, B1, B2, right? But the Lagrange multipliers are just helping you exist such numbers such that. So this is enough to you can certify this case.
Yeah.
Okay, and that's like 6 digits or something.
Yeah. Right.
Okay.
Yeah. 7. Yeah. And
is that any good? Is that I have no idea. Is that 6 digits is good?
oh, so yeah, I mean, in this example, the 7-digit was the kind of the minimal like a precision that we can have. So if you have a 6 digits, alpha theory starts to be failed. So that's the reason that we use the 7 digits in here.
Okay.
But in interval arithmetic, we can have 10 to the negative 2, which is the box contains. This is a side length.
This is much better.
In terms of like a precision, we can allow to have more crude input. We can
So
have.
it's a better certification method.
But I'm gonna compare these two methods later. But it is hard to say that because alpha theory usually certifies more. Because alpha theory certifies that quadratic convergence of
But certification is a
I mean in terms of precision, it is better.
I don't care.
Right.
Yeah, that's a separate problem. So
Right.
For certification, I want it as big as possible.
Right.
If you can certify with a mile and radius, that's even better.
That's true. Yeah, that's true.
So that's how we should evaluate.
Right. In terms of that, Krawczyk method is better.
That's my point. Yeah.
Yeah. So I mean, just like the question before, so probably it's gonna be natural to think about comparison between two methods. So we also consider this kind of capital F system equations, and we also have this approximation root, and we're gonna use both methods in here again, but we're gonna round this approximation on the several decimal places, and we're gonna observe which method start to be failed first. So here's the results. So Krawczyk method even succeed with the approximation rounded at the decimal place 1.
How did you get that approximate?
Oh, this is obtained from some numerical solver. Probably you just use Mathematica. So Krawczyk method succeed even with the decimal places 1, but in order to succeed with alpha theory, we need more precision. And this is because, just like I mentioned, because interval arithmetic usually allow to have more crude input, and also alpha theory give us more information about the quadratic convergence also.
Decimal places of what?
Decimal places, which means that decimal places 1 means that we rounded this solution.
Just take 0.4, 0.5.
Yeah.
That's one decimal place.
Okay. So this is all about regular solution. So now we will think about the multiple roots. So in order to think about the multiple roots, we need to think about what is the difference between the multiple roots and the regular roots when we solve that using a numerical solver, and we need to understand what is the challenging part in here. So let me just give a toy example here. Capital F of x is equal to x squared. We also have x is equal to 0 with the multiplicity 2. But I will solve this using some numerical solver. I use Macaulay 2. Then we're gonna get these two solutions. But we should observe that this actually has a two solution, which is not one solution, which means that we got a cluster with two roots. So let me just describe this using a diagram. So we have a capital F, which has a solution at the origin. But when we solve this system using numerical solver, now we got 2 points in here, which is close to each other. But we can understand these blue 2 points as solution of this capital G. So what is happening when we use the numerical solver in order to deal with the multiple roots is, even though we have capital F, but we have a two solution which is close, which is the capital G, and this capital G is really close to capital F. This is what is happening when we deal with the multiple roots. So let me just deal with a little bit more complicated example, a little bit more tricky example. Let's say that we have a linear term x minus 0.1. And of course, we have a multiplicity 1 in here. If you solve this using a numerical solver, then we're going to get this kind of numerical root. And let's say that we switch this into A. And let's suppose that A is really small, like 0.00001, something like that. In that case, we're going to have this A in here and these 2 points in here. But if we draw this into the diagram, probably we can understand this. We're going to have these 3 points in here. But probably we can understand these 3 points as just a cluster of the 3 roots, which are approximating the multiplicity 3 roots. Or we can also understand this as just a one regular root and the cluster of the 2 roots, which are approximating multiplicity 2 roots. Which means that if you solve system using a numerical solver, we don't know what is the multiplicities. It can be understood as 2, or it can be understood as 3. So that's the reason that we need to think about the concept of separation bound, because we want to isolate our multiple roots and other roots, when we want to guarantee that other roots are actually outside of the separation bound. Yes?
I'm sorry, this is a question about the previous part. Can I still ask?
Yes.
So with the alpha certification,
Yes.
do you also, here you're working only in the real domain, but with alpha certification, you certify that the root is real.
I mean, yeah, we can, even for the Krawczyk method, we can also work with the complex.
Yeah, but no, my question is, you have a real root, or an approximation of a real root that is real. No, sorry, you have, the approximation you have is real. And when you certify it with alpha certification, does it certify that the actual root is also real or not?
This alpha theory itself cannot do that, but we can apply that alpha theory to check the realness of the root. We can do that. Yes, we can do that, but not in this way. Not exactly in this way.
Thank you.
Now, let me step back one step and just ask a general question. You know, the difference in real and complex, generally speaking, is very tough. You need very different techniques, especially multivariate system. And yet, using these interval methods, Newton type methods, Krawczyk is just a Newton type method, allows you to easily switch between real and complex and almost no consequence. It's very surprising in some sense, right? Why is that? And just a general question. Because if you look at the algebraic theory and everything for certifying roots and detecting, it's a completely different theory, right? For a real case, you have Descartes' rule of signs, Sturm's sequence theory. That's only the real case.
I will say that's because Newton sees the complex just as R2. No?
That's what you think.
That's my explanation.
Yeah, that could be the reason. I'm not quite sure, but there's methods for counting roots. Well, this is certified roots. For counting roots, there's no way the two methods are completely different. There's no way you can. Yeah, so it's curious then.
Okay, sure. So
Actually, I don't like the way you pose this problem. It's it's like a red herring, because you give a single point and say, is this a multiple root or a simple root? And then you say, okay, well, if you look at this, it looks like one root. Because you really cannot look at single number and say what you're trying to certify. You have to also give a radius.
yeah, okay, yeah.
Then you can distinguish the two. So
I see.
try to give a fairer way of building up the question.
I see.
Okay. Anyway, let's go on.
So now we want to construct a separation bound which isolate in the multiple roots. So before we construct this separation bound, actually, probably we can illustrate what's helpful to think about some desired property that we want to have inside our separation bound. So now we have a capital F, which is the polynomial system. Now we will just go back to polynomial system for a while. And again, x star is just the exact root of the capital F, which is a multiple root. Let's say that we have multiplicity n. Then the first property is, of course, isolating other roots. So if there is other roots, which is denoted as y, then of course this y should be outside of the separation bound. So if you see this picture, this y, which is other root, should be outside of the separation bound. This is the first property. Second property is quite similar to the first property. So let's say that this y is now a point inside our separation bound, which is close to x star. Then in that case, we want to say that capital F of y and norm of that is greater than or equal to some non-negative number, which actually, this is similar to first one, but which also gave us an approximation of the lower bound for the capital F of y. Okay, so this is quite useful property. And the third property is, let's say the capital G is the scarce system, but let's say the G is close to the capital F. Then in that case, inside our separation bound, then we want to have exactly multiplicity many roots inside our separation bound.
Does M depend on Y? M?
This
big
one?
M, big M.
Depends on y? Yes, it depends on y. Yeah. It depends on the distance between x and y. So these are the properties that we want to get for the separation bounds. Okay? So let's look at this kind of previous works about the separation bounds. So Didier and Shuk in 2001 they were studied about the separation bound for the multiplicity two roots, and Li Hong and several of their students worked about the separation bound for the multiple roots with the dimension of the cone of the Jacobian is equal to 1 case. Okay, so you're going to be really good if we can just deal with this kind of separation bound for all kinds of multiple roots. But the multiplicity structure is really complicated, so we want to restrict ourselves to some kind of simpler cases. So we want to define simple multiple root. So in order to define, before we define that, let me just introduce the deflation method first.
Can you go back to the
Yes.
previous slide?
Yes.
So dimension of the kernel of f prime is 1. Is that so? How strong a restriction is that? It covers the do-shoot case, right?
Yeah, it covers the Shuk case
In general, what does it cover?
and we can also have, when we have this dimension of the kernel Jacobian is equal to 1, we can have a multiplicity like 2, 3, or 4, or 5. We can have
Right.
arbitrarily many.
But there are some restraints, right? The dimension is stronger than this. Just trying to understand what that. Can you give a concrete example just to help understand what dimension kernel of?
like if you have.
Oh, I see. The Jacobian, which is f prime,
Mhm.
has codimension 1. That's what.
Yeah,
you said.
right, exactly. Yeah.
Okay, that's. Okay, I see. Okay.
So in order to define the simple multiple roots, I will talk about the deflation method. It is just like recovering the quadratic convergence of Newton's method for isolated multiple roots. So if you have a multiple roots, it is usually so when we have a Newton iteration, we need to have an inverse of the Jacobian. But when we have a multiple roots, Jacobian is no more invariable. So we cannot define a Newton's method, but deflation method makes us to have a quadratic convergence of the isolated multiple roots. How can we do that? We introduce more variables and more equations, and then we construct a more augmented system, which is larger size than the original one. Then you're gonna have isolated roots, which is probably less multiplicity than the original roots. So this is the one, but let me just introduce a little bit more with detail. We use the algorithm of Anton Lakin and Jan Rochelle, the Eiling Zhao, which was suggested in 2006. So we have capital F, which is a scalar polynomial system. We have isolated multiple roots x star. Now we have a dimension of the cone of the Jacobian is equal to kappa. So from now on, kappa is the notation for the dimension, codimension of the Jacobian. Okay. So we need to have some random choices. So B is the generic matrix with this size, and B is also a randomly chosen vector. And then we can construct this kind of augmented system, which is denoted as capital H. Then there's a unique vector lambda with this size, and we can construct this kind of solution, which is isolated 0 for this H, and probably multiplicity of this x star lambda is less than the x star of the capital F. So if it still remains singular, then we're gonna iterate this deflation process multiple times in order to until we get a regular solution. And it is also known that if you multiply multiple times, then we're gonna get a regular solution.
So say that again. So
Okay, so
can you give a more concrete example?
about deflation method.
Yeah. What you're doing?
So okay, how can I say, so when we have some kind of multiple roots, we introduce more lines or something like that in order to decrease the degree of decrease the multiplicity of the roots in there. So this is such a technique. So decrease the multiplicity of the roots.
Introducing lines.
Introducing more variables and more equations on the equations. So we are in geometric description, we are thinking about ideal, which is generated by this more equations and more variable. Then you're gonna be some kind of tangent bundle, then stratified tangent bundle, which has probably have a lower multiplicity than the original solution.
So you keep the F unchanged, right?
Yeah, we don't change the F, but we introduce more system, which has some random choices in here.
And could you explain random choices?
We just choose some matrix with this size just randomly.
So what's the final number of variables you actually introduce? Kappa,
This many variables.
n minus kappa.
Yeah.
So at most you double the number of variables.
Yeah, so we're gonna increase the size of the system.
But at most by 2.
Yeah. So the problem is when we apply this deflation method many times, then we need to deal with the larger and larger system than the original one, so which is computationally expensive.
Right.
So we're gonna come back to this point when I suggest some open problems. But this is a deflation method. Now we can define simple multiple root.
Could you go back?
Yes.
So could you explain precisely again generic?
Oh, generic means that like we want to have
It's a theorem, right?
yeah, right.
So could you say precisely?
Oh, I see. So we're gonna when we chose this matrix and vector randomly, then with probability one we're gonna get the regular roots.
But randomly, so what's the meaning of random? And what's the meaning of probability one? Is instead of probability
so we just want to choose a matrix outside of some major zero set, outside of the major zero set. Some kind of the codimension bigger than one set of the codimension bigger than one.
Okay.
So some kind of, if you have a plane, then we want to avoid some line, special line.
But you don't know in advance which one. Right?
Yeah, of course. So, of course, it is possible to have a really bad example, but with the probability one, we can just, when you just choose randomly, then we can guarantee that this method will succeed with probability one. So now we can define simple multiple roots. So when we have isolated multiple roots, it will going to be called as a simple if and only if this deflation process terminates by only one iteration. So in terms of deflation method, this is a simplest case. Okay. So we have really nice characterization for this simple multiple root. So let's say that we have an x star, which is a multiple root, and we have a kappa in here. Then x star is simple if and only if, just like we have a random choice for the vector and the matrix before, so we also have a random choices for the orthogonal basis.
Simple means isolated, right?
Yeah, isolated.
Simple usually means multiplicity 1.
Right. So
isolated means you have a single root but high multiplicity.
right. Oh no, but simple multiple root is this is term that we just made. So
right. So when you say simple here, you mean what?
So it sounds like contradiction. Simple multiple.
Yeah.
yeah, right. So that's
Why didn't you say simple root means
right. So
single root multiplicity 1, and isolated root means there's a single root but it may have high multiplicity.
right. We coded this as a simple multiple root because among the multiple roots, this is the simplest case in terms of deflation method. Because
so it's just a title.
yeah, just a title. It is just it's a terminology.
And it's
that we define.
related to your deflation process.
Yeah, in terms of deflation process, because you're going to terminate by only one iteration.
And is your deflation process really so sort of geometrically meaningful that,
Yeah, it is
it really geometric? What's the geometric meaning of
deflation.
having 2 iterations, for instance?
Oh, 2 iterations. Sometimes. So when you think about the points inside the tangent bundle, probably you're gonna get a multiple roots. So if you apply the one deflation process, then if your multiplicity does not drop, then we should apply that once more. If you multiply that enough time, then eventually it will gonna be the regular root. It will gonna be the simple root. But when does happen? Actually, I don't know. It really deals with the really complicated multiplicity structure.
Right.
It really depends.
Right. In algebraic geometry, right? I mean, curves and so on. That there's this idea of blow up, right?
Yeah.
And you use this blow up, then something happens, and then you keep blowing up and this forms a tree structure. Right?
Yeah.
Is this related to blow up?
I don't know. I don't know. So now we gonna choose some orthonormal basis. Then we can construct this Colli A operator. Then when we have a simple multiple roots, this Colli A should be invariable with the probability 1. So the reason that I say mention of the probability 1 is we need to choose some random orthonormal basis for the kernel. So let me just explain about this Colli A a little bit more clearly. So we have 2 terms in here. First term is the Jacobian, which is a matrix. We have a second order derivative, which is the 3 tensor, but we multiply with the orthonormal basis, so it becomes a matrix. So this is just a linear operator, but it becomes invariable when we have a simple multiple root. So let me just give so this definition, now we can extend our definition onto the analytic system, because if you think about the Taylor expansion of the equations inside our system, then locally we're going to have the same multiplicity structure, so we can also define this kind of simple multiple roots onto the analytic system also. So let me show you the example. We have a 3x3 system of equations in here. We have sine function, which is an analytic function. We have a simple multiple 0 at the origin. Kappa is equal to 3. Multiplicity is 11. Now we choose 3 vectors in here. Then we can construct this Colli A in here, which is invariable. So this theorem is really nice because if you remind the gamma parameter in the alpha theory, we have inverse of Jacobian, but multiple roots, this Jacobian is no more invariable. Now we can define this gamma kappa using this A in here because this is invariable. Okay? So this gamma kappa is always well defined when the X is a simple multiple root of the capital F. So also let me just introduce one more parameter which is called small d in here, which is the smallest positive root of this equation in here. So this equation always have positive real root, so we will just choose the smallest one. So this is just the parameter. Now we can construct our separation bound. Let's say that we have x star, which is a simple multiple root of capital F. Then let's say that y is just another root. Then the distance between y and x star is at least this number. So we have ball centered at x star, which is this many radius, and the y should be outside of this one. So this is the first property of the separation bound. Second property is we want to approximate the lower bound of this capital F of y, which means that we have the same setting, but let's say that this y is now a point which is satisfying this one, so which means that they are close enough. In that case, the norm of the capital F of y is greater than or equal to this number, so we can approximate the value of this capital F of y.
Okay. So this is the evaluation bound.
Yeah, right. For the values inside the some bound.
Is at least d times.
Of course, it depends on y.
That's a distance from the root. Okay.
So now we need to think about the third property of the separation bound. So in order to talk about that, we need to think about the concept of distance between two systems. So we can just define the distance of the two systems around this point locally like this. Then using this kind of distance, we can have third property of the separation bound, which means that we have simple root with now we have a multiplicity m in here. In this case, when we have a positive number, capital R, which is satisfying this one, then if you think two systems which is really close enough, something like this, then there are this exactly multiplicity many roots of this capital G inside the separation bound.
So this R is whenever x and y are less than R apart, too many things going on. Sorry.
So if you remind the situation of the capital G, so when you solve the system equation using numerical solver, then you're gonna get a solution of capital G, which is close to capital F. So this is describing that situation.
Right.
So when we have a separation bound, numerical roots will be also contained inside that.
Okay.
So, but because we have multiplicity in here, but of course when we solve the system numerically, we don't know what is the multiplicity of the multiple roots. So we want to have at least some small information about this multiplicity. So when we have kappa, which is a codimensional Jacobian, then this multiplicity is at least 2 to the kappa. So this gave us a lower bound of the multiplicity. I think that this is a quite well-known fact in the commutative algebra community, but we couldn't find any reference for this one, so we just proved. Now we want to certify our solution using this kind of separation bound. Now we have some analytic system. This is x is just a point, so probably the numerical root that we want to certify. Now we would just choose some orthonormal vectors. We don't need to follow these details in here, but what I want to do is we just want to make a system capital G which is close to capital F. Then we can have some linear operator which is A minus H, which is invariable. Now we can define gamma kappa with the three inputs, capital F, X, and V. Using this one, we can have this following theorem. So we can compute these values in here. So if this inequality is true, then capital F will have at least 2 to the kappa roots inside the ball center that X with this radius. So we have 2 to the kappa roots because we know that multiplicity is at least 2 to the kappa. Of course, we don't know what is the exact multiplicity, but we know that at least 2 to the kappa roots should be inside this ball, inside the ball center of that X. So I want to show you how to use this in terms of real certification problem. So let's say that we have capital F, which is given in here. It actually has exact root at the origin with kappa is equal to 3, multiplicity 8, but we don't know. But we just solved this using some numerical solver. Probably we're going to get a bunch of numerical solution, especially around the origin, then we're going to get 8 solutions, which is close to each other. We're going to call one of them as T. Then we can just compute this inequality, then we can check that this is true. It means that we have a ball centered at T with this radius, which contains 8 roots of the multiplicity of this capital F. So if I just draw the diagram in here, now we have a root, now we have a ball centered at T, which contains 8 roots of this capital F. But we know that distance between origin and this T is, of course, less than this radius. This X star should be contained inside the original separation bound. So how can we complete this certification? We were going to do this for other 8 roots in here. So if you think about this ball centered at T2, second multiple roots, then you were going to contain also X star. T3 also contains X star. Just like this, if we do the 8th root in here, then we're going to contain X star in here. Now we can complete this certification. So I want to suggest open problems before I finish the talk. So if you think about the regular roots case of the analytic function, we just certify the roots using some oracles. So next question is, can we find such oracles for these kind of analytic functions? For example, like holonomic function. As I mentioned before, holonomic function is multivariate setting, multivariate version of the definite function. So this is a linear PDE of the polynomial coefficients. So it is also already known that the major series also exist for this kind of holonomic function. And also, but we don't know how to evaluate the various holonomic functions. So one hope is we can also think about D-module theory, because this kind of holonomic functions really closely related to this D-module theory. Also, there is one known way to evaluate this holonomic function, which is called holonomic gradient descent, which of course works nicely, but the problem is this holonomic gradient descent is not certified. So there's no certified way to evaluate these holonomic functions yet. So, and we can even more ambitious on working on the Pfaffian functions. So it is really a little bit tricky to define what is Pfaffian functions in here, but it is some kind of a function obtained from the chain related to the differential equations. So if we can deal with holonomic functions, probably we can also deal with this kind of Pfaffian functions. What about the multiple? What about the open questions in the multiple roots? So maybe we can think about the Newton iteration for the multiple roots. So if you think about the deflation method that I mentioned before, in order to apply deflation method, we need to think about augmented system, which means that we need to have a larger system than the original one. Which means that if you apply the deflation process multiple times, then it's going to be really computationally expensive. So if we can define into an iteration on this multiple roots, probably you're going to be computationally really much better, because we can just use our smaller original system. So I want to suggest this algorithm. Of course, we don't need to read this one, but in the second part, we just use curly A, the operator that I suggested before. So instead of this Newton iteration, we can just use this curly A operator instead of that. Then we can define some kind of modified Newton's algorithm. And I just call this as a prototype theorem because we are still working on this one. But we can show that with this algorithm, actually, we can get the quadratic convergence of this revised Newton's method. Okay. Let me stop it here. Thank you. It was way longer than I thought.
You took 2 hours?
No, but 75 minutes.
Yeah, a lot of great problems here. Yeah, so
questions right now. So if you-
Yeah, you can.
Yeah. So how do you so if I give you a poly disk, how do you confirm that there are, how do you count the number of roots in a poly disk?
Oh, that's the problem that I couldn't answer when we work on this problem, because that's the reason that we just at least want to know the lower bound of the multiplicity. So we don't know.
But I guess somehow degree theory gives that information. It's just that I don't know of any way to effectively use degree theory.
Some kind of intersection theory.
No, it's sort of, by integration, right? We know that basically if you integrate around a region, you can count the number of roots in there. Well, in a complex univariate case. But degree theory, I think, generalizes this to all dimensions. And developing that as a tool to count, I think is really absolutely critical for making progress in all these things.
Yeah.
Because I said I don't like your assumption that you say, oh, I know I have a root here of multiplicity M. You actually never know that.
Yeah, right. That's
That's
the point. That's the problem.
So I mean, basically along our line of doing clustering, you have to begin with, you have to be able to count first. If you can't count, you can't really do serious computation, because nobody's going to tell you, yeah, you have exactly a single root of multiplicity 5. No, you don't know that. But counting is a meaningful problem regardless of multiplicity. I think we should try to think hard on this.
So can I ask a question related to this? Can you show the last slide? So your A Calais inverse of Calais, can you show again the definition?
Yes. I think we should go back quite far. Sure. Okay, let me show. Yeah, this one.
So here, where does the multiplicity appear? It's K, kappa, right?
Yeah, right. This is the dimension of the co-dimension of the Jacobian. So multiplicity does not work. So in the simple multiple roots, we can have arbitrarily high multiplicity. So multiplicity cannot be bounded.
So it's the dimension of the subspace spanned by all the differentials that vanish on X, right?
Which one? This one? This? What?
So you say it's the codimension of the Jacobian.
Mm-hmm.
Okay, so it's the codimension of the Jacobian. So can you, provided that you managed to prove the last theorem you were showing us, can you imagine an iterative process like you?
We proved the quadratic convergence.
So you could find or guess the multiplicity by constructing different Calais, and since you don't have, while you don't have the quadratic convergence, you change the Calais, and at a point you should be able to construct a Calais.
Oh, this A, even though we don't know what is the exact root.
I was trying to elaborate on what she said and imagine a test to count the multiplicity. Meaning you construct several, like you do it, you construct different matrices Calais for different multiplicities, and for the correct multiplicities you should have something that converges quadratically.
Oh wait, but this Cayley A does not relate it to multiplicity. it only relates to the kappa. Kappa is the codimension of the
Okay.
Jacobian. So,
So you cannot.
it does not give you any information about the multiplicity.
Okay, so
So, I mean, in order to answer the cheese question, maybe we should think about something else, like just like degree theory or some numerical techniques.
Very nice. All right, thank you again.